Good afternoon, everyone. Welcome to our panel discussion on the topic Sustainability with Wasm, Faster, Greener Computing. I'm Saloni Narang, moderator for today's session. I'm thrilled to have such a distinguished panel of experts with us, Danielle, Saiyam Pathak, Shivay Lamba. And we had one more, Rishit, but he couldn't join us in person, but he has given his inputs and contributions. Together, we'll explore the transformative potential of WebAssembly, WASM, in driving sustainable software development practices. So why not let's start with the introduction first. Shivay, would you like to go first?
Hi everyone, I'm Shivay. This is my second Wasm I second panel, so super excited. But I have been a core contributor to the Wasm Edge project and have been working a lot on AI inferencing with WebAssembly, working also towards how we can optimize machine learning inference on Edge with link time optimizations and ahead of time compilation for like NERF models. But outside of that, I work as a developer relations engineer at Millisearch. Yeah, super excited for this panel.
Hello everyone, my name is Saiyam Pathak and I work as a field CTO at Civo. Also, I have a community called Cube Simplify where I just launched, not just launched, but in January I launched a WebAssembly course that is going good with Rishit, who is also one of the co-presenters. And yeah, so Civo is a cloud native platform and for managing, like we provide the infrastructure layer and stuff. And I'm also CNCF ambassador and good to see old friends, new faces over here. So excited for this session as well.
Hey, I'm Danielle. I work at Fermion, where lately I've mostly been working on shipping SpinCube, which a lot of people apparently saw yesterday, so that's neat. Also, one of the co-chairs of the CNCF WASM working group, trying to sort of bridge the gap between all of the WebAssembly people and all of the cloud people, because people weren't talking to each other, and that kind of sucks. Yeah.
Good. So, as we all know, the software has been eating the world, and lately, with the rise of AI boom, we can say that new AI models every day is eating the world. Now, these software, AI inference of the model, the way we interact with it, everything runs on the server somewhere around the world. With more powerful applications comes the demand for more powerful servers. With more powerful AI models comes the demand for more powerful GPUs. Now, these servers and GPUs consume power, and the rate at which this demand for data centers are rising. GPUs are rising. It's going to be difficult to keep up with the supply of energy required to run them with our current approaches. So these all come at the cost of environment, and the need for sustainable computing has never been more critical as we strive to reduce our carbon footprint and optimize usage efficiency. As per the stats from Climate IQ, 2.5 to 2.7% emissions are by data centers, and 4 to 5% global is by software as per State of Green Software report, and is likely to grow up to 14% by 2040, which is definitely concerning. To give you the context, the aviation industry contributes only 2.8% global emissions. So let's discuss how WebAssembly comes into the play. But before we dive deeper, let's set the stage by understanding what WebAssembly is and why it is a game changer for sustainable computing. I'd like to turn on to one of our panelists to provide brief introduction to WebAssembly. Saiyam, could you please take that?
Yeah, sure. I think those were some very interesting numbers out there. If you see the data center consumption, which sits at 2.5 to some percentage with respect to aviation industry, that sits at only
2.
similar
2.8%.
Yeah. So those are some concerning numbers, and with the rise of these, we have to figure out what technologies we are dealing in, how each technology can play its own role with the sustainability, and we, putting the political aspects aside, as software engineers, can do our bit in in the sustainable ecosystem. So WebAssembly, how many of you are already aware of what WebAssembly is and stuff, so that we can keep it short? Yeah, it's Wasm I, right? So people should be kind of aware of. Anyways, if so, WebAssembly is basically, in very simple terms, is a compilation target. It's a universal bytecode format that a lot, like, it's not something which has happened immediately. It's years on years of advancement, starting from JVM that also tried to be the same, and then ASM.js, and then starting off with all the standards that has been written in W3C, and all the specs that have been written, all the runtimes that came into the picture. So WebAssembly is a compilation target, universal bytecode, portable, that runs on any platform. So think of it as you have written some code in any language, you should be able to compile it to a file called a binary called .wasm, and that should be able to run on any system which has the WebAssembly runtime. So you have specification, and the WebAssembly runtime makes sure that it's properly sandboxed, so that it's super high secure. Since it's very native to the machine code, so it's near native performances, so that makes it super fast. Also, again with the similar lines, since it's the machine very close to the sits closely to the machine code, it's also lightweight in nature. So I think all these definitely contributes to all the factors when we talk about running the softwares, which definitely we'll be talking throughout the panel, in the sustainable ecosystem. But yeah, WebAssembly in a nutshell is a universal bytecode format that you can run on any system, super lightweight, and there are 20 plus programming languages that supports WebAssembly as their compilation target. So that's what WebAssembly is.
Thank you, Saiyam, for the comprehensive overview. Now that we have a better understanding what WebAssembly is, let's dive into some of its features, where it is used today, and it is very important to understand the landscape we are in today. Shivai, would you like to take that?
Sure. So I think a lot of the features were already covered by Saiyam, but primarily, again, just kind of reiterating on the two major aspects, which is the universal bytecode format, and that can run on systems across not just the web, but also you can run it on the edge on cloud, right? And that's, I think, one of the biggest use cases why we have seen a huge popularity and rise in adoption of WebAssembly across the entire ecosystem. So kind of started off as a browser technology. We saw early adopters where a lot of companies were using it for building games to be able to run in the browser, and then video editing software, and like Adobe getting it, Google Earth using it for doing like more 3D and physics optimized workloads inside of the browser. But since then, we have seen a lot more of usage in the cloud. Today we have like Spin Cube project being released, and of course there's an option across different cloud platforms being able to run Wasm workloads with the Wasm shim, and then serverless workloads with fermions as well, and then and just being better because of the cold start time that is a lot less in comparison to your standard serverless workloads. So of course, like, all these use cases are there, but of course the biggest rise that I personally feel is going to be the changing point is AI inferencing, right? So today, whether we talk about LLM inferencing on the edge, there's the Llama Edge project by Wasm Edge community, which I've been a core contributor to as well. And again, like, the biggest use case that we see is this is a time of inference, right? The ability for the Wasm module to spin up and close as soon as you end up doing that execution. That's what is the biggest game-changing feature, and that's what we're seeing for a lot of these use cases where you want quick inference as soon as possible, get that done with the Wasm module, shut it down, so that ends up saving your cost as well, right? So yeah, I think like we'll be exploring more towards how it kind of expands into the different language spectrum as well. But yeah, super excited for especially the AI inferencing part of things.
Those are some interesting use cases. So extremely low startup times, smaller binary size, portability are some of the key features. I want to highlight the software carbon intensity equation over here. SCI is equal to O plus M per hour. So is a measure to quantify the carbon emissions of a software system. In this formula, SCI is software carbon intensity. O denotes the operation emissions from running the software. M stands for emissions from manufacturing and delivering the software. R is the reference unit, which could be anything like number of users, API calls, or ML training runs to normalize the carbon emissions. This metric helps in understanding the environmental impact of software. Now, there are papers that also shows energy efficiency of programming languages. Daniel, what is your take on the energy consumption for various programming languages that you might have benchmarked, and then how WASM changes the equation?
So the interesting part here is there was a study about a year ago that studied the difference in efficiency of programming languages when running natively versus inside Wasm time and one of the other runtimes, I don't remember which, that showed even back then a marginal couple of percent difference in energy consumption of an individual execution unit. But the place where WebAssembly makes that interesting is most software isn't actually responding to events all of the time. So in Azure Functions, for example, the average function receives less than one request per minute. But the rest of the time, it's still running. It's still, listening on a socket. It's still doing random background, like garbage collection, whatever. And that kind of sucks. Like, that adds up to a whole lot of compute. And so when you move to an event-based compute model that a lot of WebAssembly runtimes are built around, you change that equation. Because it's no longer how efficient is this one piece of thing. You can change it to be how dense can I make my overall system. Your average server sitting idle uses somewhere between 30 to 60% of its maximum power when doing nothing. Which means if you have a whole bunch of servers waiting to do one request a minute, that's a lot of power. If you can compress all of those applications onto a single server, well, now you saved yourself a whole bunch of power. And if you've got data centers in Europe, you saved yourself a whole bunch of coal. And that's good. So that mixed with the fact that the average Kubernetes node, for example, is 60% idle, it's kind of embarrassing.
Okay, thank you, Daniel, for your insights. Now let's move towards WebAssembly impacting the sustainability. Shivay, you mentioned the features of Wasm. What is your take on Wasm's impact on carbon emissions?
Yeah, I think in terms of measuring, it's really important to measure how much energy is being spent whenever you are running any sort of an application. So in fact, like when I actually understood this more from a deeper angle, that whenever you're actually serving any website, that's also like consuming electricity, right? That's consuming a set amount of power. Now, depending on how efficient you have made your website, it will take up, or that it will consume that much amount of power. So there's a set of experiments that were being run, which kind of compared how, if you took a standalone application like uploading a PDF file, when you're running it natively in JavaScript versus when you're executing that same code with JavaScript and WebAssembly. Now, if you're just taking any snapshot of how much energy was being spent at just one particular instance, you might find that, okay, with WebAssembly, the amount of power that is being drawn is a bit higher as compared to like doing it natively in just JavaScript or using web workers or service workers. But if you kind of look at the entire execution of the run of that particular workload that you just ran, the amount of energy that is spent, like if you're calculating in joules or kilowatt hours, that is actually lower for running it with JavaScript and WebAssembly as compared to running that same solution in JavaScript. So that's a clear metric that we see, that this the total amount of power that is consumed when running that application in WebAssembly was actually lesser. So I think like that's one of the bigger points that we look at, and of course we'll be diving deeper into some of the aspects in terms of like doing machine learning inference, because of course that's some of the trending things that you're seeing right now. But yeah, that's my take, that overall, if you're really optimizing your application and you're running it with WebAssembly, more often than not, it will consume less power, right? Even if you're like just doing a simple simple thing like running a website.
Maybe Daniel can explain more on the Wasm runtimes.
To like give that a little bit of context, when we released SpinCube yesterday, we also were talking about our work with Zeiss, where in moving over a couple of their real-world workloads, it was modeled as such that by moving to WebAssembly, they were using 60% less compute than they were previously with native software, with no other architectural changes, which is, I mean, imagine everyone using 60% less compute, right? Like, that changes those carbon emission numbers for data centers dramatically. Can we make that happen, please?
Okay, those were some insightful pointers to how Wasm and Wasm runtimes creates an impact in the sustainability ecosystem. I mentioned hardware as well as AI stuff that is going on. We need more DCs, and more DC mean more hardware. Sayam, since you are from a company that provides infrastructure, do you know anything happening in this space with respect to infrastructure?
Oh yes. So yes, that this part is pretty interesting, and I'm actually would love to talk more about it even after this particular session. So uh, when we talk about, well, obviously Saloni mentioned a lot of pointers, a lot of metrics. The AI is booming, and we need more and more data centers, and that is true that we cannot sustain the demand and supply of the data centers with the same approach that we are doing. So, also to give you another metric, so 97% of the heat, so 97% of the energy that is used by the servers is emitted out as heat. So I think this is not something that we cannot do anything in this area, but this is a very big sign of innovation that can be happen in this particular area. And that's what actually happened, and people have solved this problem. So there is a company called Deep Green. So Deep Green, what they do is it's pretty fancy and pretty rad stuff. So Deep Green reuses the heat emitted from the servers to heat up the swimming pools in UK. So, I mean, how cool is that? So, you are swimming in the pool, and that is being heated up by the servers, and somebody is running a workload, AI inferencing on that particular GPU, and that is actually heating up the swimming pool in which you are practicing and swimming. I mean, those are some of the. I mean, I mean, I was blown away when when I heard about it. Now, tying it to the equation in the Wasm IO context, in the WebAssembly context. So we have CIVO as the infrastructure provider. We have partnered with Deep Green, who have this particular technology of reusing the swimming pool, reusing the heat to heat up the swimming pools. So at CIVO, we right now, if you log in, you'll be seeing a Deep Green region. In that region, you can spin up GPUs and you can do your AI inferencing. Now, one of our biggest customers is actually Fermion, who is using it. So that's a 100% sustainable solution out there. So the electricity that is coming in and then getting reused, and then WebAssembly, all the pointers Danielle mentioned, Shivay mentioned on how efficient AI inferencing is when it is done as the WebAssembly modules. So all these things coming into the picture, so Fermion, Deep Green, and CIVO kind of gives a very powerful combination, and tying it to the angle of sustainability. So how WebAssembly comes into sustainability, hardware innovation comes into sustainability, reimagining the cloud comes into the sustainability picture. So I think this particular piece, and this is so beautiful that as creators of the products, we feel satisfied that we are doing something right, and as the end users, you can feel confident and feel okay that okay, we are training a new model or we are doing AI inferencing. It is not impacting stuff. It is actually getting reused for the community purposes, and they have also it's not, the innovation is not stopped here. So this is one of the use cases, heating up the swimming pools. Now with like this, there are other household use cases that can be catered with the same heat. It's just a matter of how how properly these particular centers will be configured, structured, so that there is a proper heat conversion stuff which is over there. It only heats up like for Deep Green, it only heats up the swimming pool whenever there is a requirement, not just 24/7. And on our side, we are doing innovation of our intelligent scheduling, like wherever the heat is required, whenever someone is running the workload, that will be scheduled on that particular GPU, which is connected to a swimming pool that is required to be heated. So I think with these all combined innovations, it becomes a really nice solution with respect to hardware, software, and the application, the WebAssembly technology that we are talking about. Shivay, you want to add anything? You have been very excited with the AI inferencing space. If you want to highlight a few pointers in this particular space as well.
So really interesting use case, and I was like super excited when I heard for the first time this collaboration. But just also going into more of the technical aspects of how AI inferencing is really empowering or, or getting empowered by Wasm, right? So I had like 3 pointers that I wanted to kind of raise. So of course, one was the aspect of AI inferencing being powered by WebAssembly in the context of how quickly a WebAssembly module gets spun up, right? So we see that with the fermion aspect as well, so that as soon as you get a request for your application inferencing to be done, AI inferencing to be done, so you'll spin up a new Wasm module and you'll be able to do the inference very quickly. So now the great thing over here is that when you're running this inside of your GPUs, you're not actually keeping your GPUs active throughout this entire time. In fact, you just need to use the GPU when it is required, and because of the cold start, like small startup time to run them, you can reallocate the usage of your GPU to some other task. So, anyways, you're doing much more efficient GPU management and GPU slicing as well. Now, another thing that we have to keep in mind is that whenever developers are working on their test setup or their development environment, now in a typical use case, whether you're talking about like even Onyx runtime, they're not like universally supported. You'll have to make certain adjustments to your ML machinery to adopt it to different kind of hardwares. And typically, like your production grade GPUs, they're not possibly it's not possible to run them even for your local inferencing. So with WebAssembly, whatever source code is being written inside of local developers, which they are writing in their local development setup, once they test it out in their local setups with the help of Wasm, you can just ship that same Wasm binary and run it inside of those production grade GPUs as well, because the same Wasm binary can be supported by multiple device architectures, right? So that's another way in which we save up costs from a sustainability angle, that you don't need multiple GPUs. The same source code can be run on the old device architecture that these developers are using in their local setups. And I think like the third point, which I actually got to know fairly recently, is around that right now we are seeing usage of Wasm more on AI inferencing side of things, so more high level GPU usage. But with web GPU coming into the play, right, there is a very recent WASI web GPU proposal being written, which essentially allows you to take your web GPU APIs, these standardized set of APIs, and then actually allow them to be run inside of WASI. So the great thing now with this use case is that originally WebGPU was only supported to run in the browser, and you can only access these GPU APIs that allow you to actually interact at the low level with your GPU APIs just on the browser. But with the support coming into WASI, you could basically take those same low-level APIs that are using with WebGPU, use them with WebAssembly, and then translate that into the low-level code into the hardware, whatever hardware requirements that you have. So not just focusing on the AI inferencing side of things, now you can also actually control low-level architecture of devices and get support for low-level APIs for GPU with WebAssembly. So that expands your use case even further outside of just AI inferencing. So I think like that's one of the coolest proposals that I'm really looking forward to. It's still in its very nascent stage. So I think the biggest challenge right now is to translate each and every API and make it available inside of WASI and get all the types supported. But this will truly be a game changer if you're looking outside of AI inferencing applications as well that require you using GPU. So, this could be used with the SpinQ project potentially, and, use it for in like connecting with the GPU drivers from NVIDIA and add access to GPU to Wasm inside of your Kubernetes clusters as well. So I'm really looking forward to this development.
Well, those are really thought provoking discussions by our panelists in the field of how WASM software and hardware tooling is there to create an impact of the environment sustainability. We will try to keep some time for the audience for Q&A, but before that, let's hear from our panelists on 1 minute quick conclusion about where they think things are moving in this space. Let's start from you only, Shivay.
So yeah, I think like in terms of sustainability, as we already saw that there are some use cases in terms of just making sustainable architecture. But I personally come from an AI inferencing background, so I'm super excited for just making that more efficient. And as I just kind of covered with this web GPU stuff, I'll be probably one of the first adopters to start using it and see how we can make that more efficient for even running on Kubernetes clusters. Because I know like Kubernetes clusters, they take up a lot of compute. So if we are able to make that more efficient, that'll be a major win.
Yeah, so the all like sustainability is all over the place. If you are writing software and if you're in the infrastructure space, you can do a lot. If you're writing software, you can do a lot. Even if you are one of the platform teams who is creating the Kubernetes clusters and giving to the team, you can have a lot because there is a CNCF tag as well for sustainability, and there's a working group Greens that is aiming to have all the CNCF projects, how much they are consuming and they are putting the carbon emissions. And there are very cool projects like Kepler, Cube Green to measure the exact carbon footprint from each of the workload in each of the namespaces. So it does using the machine learning models offline, online, and it also uses, all the metrics that it pulls. So it has Prometheus and all that other stuff integrated in it. So, and then you can use again in conjunction with other projects like CubeGreen to scale down your deployment when you know the carbon footprint of specific application. So I think on the hardware side, software side, in a combination, there is a lot that you can do, and people are doing. We are hearing a lot of use cases from the companies. Even in the tag, there are a lot of discussions on how currently people can adopt a particular tool and do something when they go back. So they are trying out different tools, getting getting the carbon emissions is the first thing. The SCI formula, the green foundation that Saloni just mentioned. So all these things, how to calculate it. Then there are models, and then when you talk about capacitance and frequency, there are papers like how to map it when you are running the CPU cycles and the RAM and stuff. So how do you map it, the frequency and capacitance, which are not direct one-to-one in the software ecosystem. So like this, I think things are going pretty fast. And also we should be like careful in whatever we are deploying, using. Just a thought. Plus, the EU government is kind of putting out some laws that every data center out there has to kind of give what their carbon emission is. So there are government regulations also behind these. So yeah, that's my take on it.
I'm really excited that for, practically speaking, the first time, there's a real path to delivering actually sustainable software without changing your entire programming model or dealing with, writing C because, well, if you really care about language efficiency, the answer is still write C or very carefully write Rust. And I'm not about that life. Like, I like being productive. And so now with WebAssembly runtimes and tools like SpinCube, wherever you want to run, you can run efficiently. And that is awesome. And then you combine that with some of the work that some telcos have been doing to reuse old phones. I think it was Telefonica in Spain, actually, that pulled a whole bunch of old Pixel phones and gave them a second life doing as like a mini data center. When you consider that you can run WebAssembly on basically any architecture that is feasibly still shipped in devices, aside from weird embedded stuff, and even then, there's a lot of work to make that happen. You can truly write stuff and run it on anything. And maybe we don't have to, throw a whole bunch of cobalt in a pile somewhere.
Okay, so we just have 1 minute left. I will open the stage for Q&A. Any questions to our panelists? No. Yeah.
Usage. So we So even if you talk about the carbon emissions, you're missing the energy grid usage. So you could have solar panels, hydro power, and that's all carbon neutral, but you're still missing the energy grid usage. So if you're measuring carbon, you're kind of pushing the goalpost a little bit away from sustainability. Because we have, I think in the US, 17% of power is used by data centers right now. And that is a strained grid. So what are your perspectives on fixing that as well?
És amb el set, perquè diu que no els hi ha sonat. Ja està. Vinga.
I can take that one?
Yep, sure.
So that's a big part of where increasing density manages to massively reduce effective power usage by reducing the total amount of compute that you actually need. Like, you know, if you look at the SysDig, I think, did a study last year that showed showed 17% utilization on average of Kubernetes nodes. That means a lot of those servers are sat using realistically like 50% of their maximum power consumption to do nothing. And based on the numbers we've been seeing from people moving to Spin especially, just through data that I have, we can massively increase utilization. And that motivates me.
Hi, and thank you for the great panel. I have high hopes that we can finally solve this bin packing issue on Kubernetes by using WebAssembly and increasing the density. But from an user experience or developer experience point of view, what do you think are like the missing areas of improvement in order to like use this? Or are there things where we are currently not use the same techniques as we are used to, like service meshes, horizontal pod scaling, this kind of stuff?
Saiyam, would you like to know that?
Yeah, so I think so me and Sven are doing the workshop on Kubernetes, like deploying WebAssembly in production. So you're right, the day two operations, where we talk about all the observability, logging, the chaos, the service meshes and stuff, it's not that much easy to do when we talk about the WebAssembly applications. But yeah, I mean, it's Kubernetes. You should be with the Spin Cube or Wasm, all the runtimes which are there, you should be able to run the WebAssembly workloads and still use the existing Kubernetes features which are there.
And horizontal pod autoscaling, for example, does work with WebAssembly stuff through at least SpinCube. And then on top of that, we actually have a prototype of distributed tracing automatically instrumented through Spin that I'm really excited to ship. But then on a standardization level, us, Dilipso, Cosmonic, and a couple of other folks are all working on a thing called WASI Observe, which is bringing all of the observability stuff into WASI. And so then we all get it, and it's going to be awesome.
So keeping time in mind, I think we should wrap up this session. Thank you all for attending. If you have more questions, you can ask them. They'll be around. Thank you all.